Okay, so today I'm going to discuss quotient rings and then homomorphisms of rings. So homomorphisms of rings is similar to group homomorphism that defined earlier. So if you understand group theory well, you can understand very easily this video. So quotient rings. Right, quotient ring. So this is similar to a quotient group, right? So in quotient group, what we will do is, if G is a group and if N is a normal subgroup, then we will form G by N. That is set of all cosets. So yes, similarly, if R is a ring, right? R is a ring and S is an ideal. So R is a ring and S is an ideal. So we have R to be a ring and S to be an ideal. Now we are going to form a cosets, right? That is R by S. R by S, and this is nothing but S plus A, and this A belongs to ring R. Then this set will form a group, and this is called this set will form a ring, and this set is called the quotient ring. Right? This will form a ring, and this set will form this is called quotient ring. Right? So S is an R is a ring and S is an ideal. S is an ideal means it is left ideal as well as it is right ideal. So left ideal as well as right ideal. So ideal means first it has to be subgroup, and AR and R actually no definition of ideal which we defined earlier. So if it is an ideal, then you form a set R by S, and this set consists of all those members of the form S plus A, and this A belongs to R. Then this will be then this form a quotient. This will form a ring, and we're going to call that as quotient ring, right? Or it's also called as residue classes of S in R. Residue classes of S in R, right? It is also called as residue class of S in R. S is the coset, right? S is the set of all cosets, set of all right cosets. Right cosets are left cosets. S plus A means right coset, A plus S means left coset. Yes. So in this, this will form a ring. So you need to define the operation, right? You need to define the operation now. So the operations is defined like, so this will form a quotient, this set will form a ring under this operation. So whenever you are taking two elements, let us say S plus A is one element, every element is S plus A, and let us say S plus B is another element. So the resulting element will be S plus A plus B. That is, if you are adding two elements in this set, you need to add like S plus A plus S plus B will be S plus A plus B. And if you are multiplying two elements, that is, if you are taking S plus A as one element and S plus B as another element, then you have to multiply by S plus AB. So this set will be a quotient. This set will be a ring under these two operations, right? Under these two operations. That is binary operation we are defining. So if you are taking two element, if you are adding two element, you need to add like this, and if you are multiplying two elements in the set, you need to multiply like this. So this set under these two operations will form a ring. Will form a ring, right? Again, what you have to do? You need to verify that first that it is an abelian group with respect to addition, and with respect to multiplication, first it has to be closed and the result is associative and has satisfied distributive law. Again, very easy exercise. So I'll just tell orally. So first it has to be closed. So first you will verify that with respect to plus it has to be an abelian group. So let's take two elements. Let us say S plus A is one element, S plus B is another element. Then the closure will be S plus A plus B. Again, this is also in R by S, because A belongs to R, B belongs to R, and A plus B also will be in R, because R is a ring. So therefore these elements will be in R by S. Therefore it is closed, and similarly it is associative. And what will be the identity? Again, S plus 0. S plus 0 will be the identity element, and the inverse will be S plus minus A will be the inverse, right? So S plus 0 is our additive entity, and S plus minus A is our additive inverse. So therefore it is an abelian group with respect to additions. Again, very easy process, right? So just refer page number 355 and 354. So first it is closed and it is associative. and third is existence of identity. So s plus 0 is our identity element, and the inverse is s plus minus a, and it is commutative also. So therefore it is an abelian group. Now with respect to multiplication, first we need to verify that it is closed. Again you just take two elements, the resulting element is s plus ab, and since ab belongs to R, ab will also be in R because R is a ring. So therefore this element will be in R by s. So therefore it is closed and it is associative also, and again it is distributive. And so therefore this set will form a ring and it is called as quotient ring. So you just make an ideal. So R is a ring and S is an ideal of R. S is an ideal in R. This is an ideal in R. Then you form a set R by S, and this set will form a ring with respect to these two operations, right? And we call that as residue class of S in R are quotient rings. Now homomorphisms of rings, right? Homomorphisms of ring. Actually this we have already discussed, I think. Homomorphisms of rings. The mapping f from R into a ring R said to be homomorphism of ring R if f of a, that is f of a plus b is equal to f of a plus f of b, and f of a b is equal to f of a into f of b, and all the results that include for group the same part rings also. That is if 0 is an that is f of 0 will be mapped to 0 dash, that 0 is the identity. So let us say the ring f is a homomorphism from ring R to ring R dash. So these two are different rings. So if 0 is an ID of R, then 0 dash will be an ID of R dash. That is identity element of this group will map to ID element of to the on that group. So again the similar property that will is true, and f of minus a is equal to minus f of a. Whatever property that we do for group theory is same for ring also, ring homomorphisms also, right? Again kernel, actually same, actually every theorem is same. The only thing is you have to replace group by ring, that's it, right? So actually if you understand that the homomorphisms of groups, you just refer page number 356, the same what they say that what we did earlier they will do again here also, right? So it is not that I have to teach all. If you understand that group homomorphisms, there are two theorems, and two theorems is same ditto of that. Now again kernel of homomorphism. So kernel of homomorphisms you will do so kernel means actually again we already defined what's meant by kernel. So kernel is a set of all elements that are mapped to 0 dash, that is the ID element in codomain. So kernel of f. So if f is a ring homomorphism, the kernel of f. So if f is a homomorphism from R to R dash, these two are rings, then kernel of f. Kernel of f is the set of all elements in R such that the image of that element is 0 dash, where 0 dash is the identity of R dash, the same that we defined for group theory also. Now we will actually already proved that kernel is a normal subgroup and kernel is a subgroup. Now we will prove that kernel is an ideal, right? Kernel of a ring homomorphism is an ideal. So for ideal, what we need to do? For ideal, we need to verify that it is a left ideal as well as right ideal. So first we have to verify that it is subgroup, and then we need to check whether it is left ideal as well as it is right ideal. So what we are going to prove is if f is an homomorphism of a ring R into R dash with kernel S, then kernel is an ideal of R. That is, we already proved that kernel is already a subgroup as well as it is normal subgroup also. Now if f is a ring homomorphism from R to R dash, then kernel of f is an ideal, right? So for if group homomorphism, the kernel of f is normal subgroup. Same, you are only changing the terms. If f is a mapping from G to G dash is a group homomorphism, then kernel of f is a normal subgroup. It's an important theorem which we proved. Now similarly, if f is a ring homomorphism from R to R dash, then kernel of f is an ideal. Kernel of f is an ideal, right? So this is the one we are going to prove. So for ideal, what we need to do? For ideal, we need to show that let us say the set, let us call the set has to be equal to S. So kernel of F, I am denoting by S. So you just take an element, you just take one element from here, one element from here. Let us take an element A. And let's take an element R, right? So we need to prove AR belongs to S and RA belongs to S. This proves that it is left ideal as well as right ideal, and then we need to check it is a subgroup, right? So for subgroup, what you need to do? The one step test, A minus B belongs to S. So this is the step for a subgroup, right? So you just take A comma B belongs to S, and you just say A minus B belongs to S. Then this S will be a subgroup, and then you need to show that it is an ideal. For that, you need to show these two conditions. So this will guarantee the subgroup, and this will give the condition for ideal. So we are going to prove that the kernel of F is an ideal. Theorem: if F is a ring homomorphism from R to R dash with kernel of F is equal to S. So I'm writing the set to be equal to S. Then S is an ideal. S is an ideal in R. S is an ideal in R. So what is S? S is the kernel of F. So kernel of F is set of all x in R such that f of x is equal to an ID element, that is f of x is ID element of R dash. So let us say this is 0 dash. So 0 dash is the ID element of R dash, right? Now let us take, we need to show that S is an ideal. Let us take first to show what is to show. To show S is ideal. For that we need to show two conditions. The first we have subgroup. Let us take two element A in S. We need to show A minus B also belongs to S, and then you just take an element A in S and R in R. So you need to show AR belongs to S and RA also belongs to S. So if we prove these three conditions, then this S will be an ideal. So we will prove the first condition. Let us take A comma B belongs to S. So A, B are in S. That means what about f of A? It is 0 dash. And what about f of B? It is also 0 dash, because S consists of all those elements whose image is 0 dash. So therefore I am taking two elements in S. F of A will be 0 dash, f of B will be 0 dash, right? Yes. Now can I write what about f of A minus B? So can I write f of A plus minus B? And we know that F is a ring homomorphism. So ring homomorphism means f of A plus B is equal to f of A plus f of B, and f of AB is equal to f of A into f of A. This we already defined earlier. So I can write this as f of A plus f of minus B, right? And this f of A, I can write f of B as f of minus B. But this is the property of ring homomorphism. F of minus A same as minus f of A. So we already know f of A is 0 dash, this again 0 dash, this again 0 dash. So this implies f of A minus B is equal to 0 dash. So this element is marked to 0 dash. That means this element has to be in S. So therefore we have taken AB in S, and then we have proved A minus B also belongs to S. So therefore it is a subgroup. It is a subgroup. Now we need to show that AR belongs to S and RA also belongs to S. For that, what I am going to do is, so I am going to prove the second, that is I am showing that this is left ideal as well as right ideal. So A belongs to S and R belongs to R. So A belongs to S means f of A is equal to 0 dash, and R keep it as it is, right? Let us take, this is 0 dash. Now what about f of AR? So I can write this as f of A into f of R, because F is ring homomorphism. I can use second condition. So f of A is 0 and f of R is R, same again, which is equal to 0 dash, right? So therefore f of AR is equal to 0 dash. That means AR belongs to S, because the image of AR is 0. That means this element has to be in the set I kernel. So therefore AR belongs to S. And similarly, what about f of RA? this is nothing but f of r into f of a, because f is ring homomorphism and f of r and f of a is 0 dash, which is again 0, right. So therefore this implies ra also belongs to S. Therefore it is left ideal as well as it is right ideal, and also it is a subgroup. So therefore kernel of f is an ideal. Kernel of f is an ideal. Now we will prove on some one more theorem. The homomorphism of a ring R and R is isomorphism. Yeah, similarly that homomorphism will be isomorphism if kernel contains only the 0 element, right. So we will prove this theorem. Actually you just have to follow the notes Krishna series book, right. So it should be very easy. The theorem 2. The homomorphism will be isomorphism if that is 1 to 1 onto. So the another condition is the kernel of f contains only the ID element, that we already put in group theory also. The homomorphism phi from R to R dash, these two are rings, is an isomorphism. This homomorphism will be isomorphism if and only if, very important, if and only if kernel of that map contains only the 0 element, right. Kernel of f contains only the, let us say I don't know mapping by phi, that's it, no problem. That is so again it's a very easy. Now what is kernel of f? So kernel of f is nothing but all those elements which are mapped to 0. Suppose if we have two elements mapped to 0, that means kernel of f contains these two elements. Surely this is not 1 to 1, because say distinct elements have distinct images, but here you can see two elements have same images, so it is not 1 to 1. So for f to be 1 to 1, kernel of f should contain only 0. That means 0 is the only element mapped to 0, right. So if kernel of f contains 0 element, then the mapping will be 1 to 1 and on to. So kernel of phi contains only the 0 element. That is, suppose if there is some other element in kernel of f, then the 1 to 1 is not valid. So for existence of 1 to 1, kernel of f has to be contain only a 0 element. Now we will prove this. So this is a if and only if condition. So first we will assume isomorphism, and then we will prove this, and then we will assume kernel of f is equal to this, and then we will prove it is an isomorphism. So solution. So assume it is isomorphism. So what we need to prove? We need to prove that kernel of that map contains only the 0 element. P is the map that we are defining. We need to prove that kernel of f contains only the 0 element. That is all we need to prove. So what is kernel? Let us call the set S, and S is the kernel of that map, and it contains all those elements in R such that phi of x is equal to 0 dash. The 0 dash is the ID element of R dash. Now we need to prove by assumption that it is isomorphism, we need to prove kernel of f contains only the 0 element, right? Yes. Now so let A belongs to S. Now what about phi of A? It will be 0. Phi of A will be 0. Phi of A will be 0. Now 0 dash. Now can I write 0 dash as 0 dash is the ID element of R dash, and we know that what will be the image of 0 dash, pre-image of 0 dash? This f of 0, right? I can write 0 dash as f of 0, because if f is an isomorphism, because the assumption is isomorphism. So for isomorphism, 0 is an ID of R, then the image will be 0 dash, which is identity of R dash. So by definition of isomorphism, we know that the ID element will always map to ID element in the codomain. So therefore I can write 0 dash as f of 0, and since by assumption it is isomorphism, so since it is isomorphism, this implies it is 1 to 1 also. It is 1 to 1. So by definition, let's say it is phi of 0, right? Because our map is fp, right? So by definition of it is 1 to 1. So therefore, by definition of 1 to 1, f of a is equal to f of b means a has to be equal to b. So since it is 1 to 1, a has to be equal to 0, right? Because we have phi of a is equal to phi of 0. By definition of 1 to 1, a has to be equal to 0, right? That means whatever I am taking an arbitrary element a in S, I am getting that element to be equal to 0. That is, kernel of phi contains only 0 element. I am taking an arbitrary element, and for arbitrary element I am getting a to be equal to 0. I am taking an element a in S. So S contains only the 0 element. So therefore kernel of F contains only 0 element. Now we will prove the converse part, right? So for converse part, assume that kernel of F contains only the 0 element. Assume that kernel of phi contains only 0 element. So assume kernel of phi contains only 0 element. So what you need to prove? To prove it is isomorphism. To prove it is isomorphism. So to prove it is isomorphism. So for that kernel of F contains only 0 element, it is an isomorphism. So for proving isomorphism, what we will do is we will prove that it is a 1 to 1, right? We will prove that it is 1 to 1 because already is homomorphism. So for proving isomorphism, we will prove that it is 1 to 1. So for 1 to 1, what we need to do? Phi of a is equal to phi of b means a has to be equal to b, right? Yes. Now let us take an element. Let us take AB in R. Let us take an AB in R, right? So suppose phi of A is equal to phi of B. Suppose I am assuming that, so for 1 to 1, f of A is equal to f of B means A has to be equal to B. So we will assume that these two have same image, that is phi of A is equal to phi of B. So what we need to prove? We need to prove A is equal to B. So can I write this as phi of A minus phi of B is equal to 0, because phi of A is equal to phi of B means phi of A minus phi of B is equal to 0. And we already know phi is homomorphism. So I can write this as phi of A minus B is equal to 0, right? Because phi is homomorphism. And this implies A minus B belongs to kernel, right? A minus B belongs to kernel of map, because phi of A minus B is equal to 0 means A minus B belongs to the kernel. So we know kernel contains only the 0 element. You can see this map takes A minus B to 0. That means this element this element must be in kernel, because kernel consists of all those elements which are mapped to 0. So this element must be in kernel. By assumption, we have assumed that kernel contains only 0. So this implies A minus B has to be equal to 0 by assumption. So this implies A minus B, A is equal to B. So we have started with phi of A is equal to phi of B. We have proved A is equal to B. That is, it is isomorphism. Already it is homomorphism. Now we have proved it is 1 to 1. So it is isomorphism. Right? 1 to 1 implies onto. Right? 1 to 1 implies onto. If these two are ring homomorphism. Show that homomorphic image of a commutative ring is commutative. Again, the same that we did in group theory. You will just refer page number 360. The homomorphic every theorem is similar to group homomorphism. Whatever the result that you proved in group homomorphism, the same for it is ring homomorphism also. You just have to recall all those results and then you have to apply here also, right? So show that every homomorphic image of a quotient ring is commutative ring is commutative. If this is commutative, then the homomorphic image is also commutative. This is already proved, I think, right? Yes. Now we will move on to the important concept, which is maximal ideals. The only thing that we left is maximal ideal, prime ideal, and Euclidean domain. So these three concepts we will be finishing the course. So maximal ideal, prime ideal, and Euclidean domain. So with these three concepts we will finish this. So maximal ideal. Actually, the theorems that are in ring homomorphism are very easy. So just refer book, right? It is not possible to solve everything in the book. Actually, you can follow very easily if you understand these concepts. So you move on to maximal ideal. An ideal yes is not equal to R. Is said to be maximal ideal in R. Is said to be maximal ideal. Said to be maximal ideal of R. This ideal is said to be maximal ideal of R if whenever U is an ideal of R, if whenever U is an ideal, whenever U is an ideal of R such that S is contained in U and U is contained in R, then either R has to be equal to U or S has to be equal to U, right? So you just go through the representation carefully. So we have an ideal. So ideal means it is left ideal as well as its right ideal, and it is subgroup. An ideal S in R is said to be a maximal ideal if whenever, suppose if you find some other ideal U such that S is contained in U and U is contained in R. This implies U has to be equal to R or S has to be equal to U, right? That is, it is the maximal. So maximal means it is the largest, right? So if these three conditions are satisfied, then we say that S is a maximal ideal. So S is a maximal ideal. So this S will be maximum ideal. Suppose if there is some other ideal such that if S is contained in U, then S has to be equal to U or R has to be equal to U. That is, it is a maximal of all those ideals. So in other words, an ideal S of a ring R is said to be maximal ideal if there exists no proper ideal contained in R which properly contains S. That is, it is impossible to find an ideal which lies between S and the full ring R, right? In other words, an ideal S of a ring R is said to be maximal ideal if there exists no ideal properly contained in R which itself properly contains S. It is impossible to find an ideal which lies between S and the full ring R, right? So S is said to be maximal ideal if it is impossible to find an ideal which lies between S and R, right? For example, in the ring of integers, the ideal 6 is not maximal ideal since it is properly contained in the ideal 3, which in turn properly contained in I. On the other hand, 5 is maximal ideal since only ideal is properly contained in itself. So what they are doing is, so for example, let us take the integers and let us take an ideal. We know that in integers every element can be generated by every element generated by single element is an ideal, right? And every element can be generated to form an ideal. So if we take an ideal, 6 is not maximal. 6 is not maximal ideal. That is, an ideal generated by 6 is not maximal ideal. Why? This will be maximal ideal if this is contained in U and this is contained in R. Then R has to be equal to U or S has to be equal to U. So what this set? This set contains 0 plus or minus 6 plus or minus 12 plus or minus 18 and so on. So an ideal S is R said to be maximal ideal. Let us take this to be equal to S. Is said to be maximal ideal if whenever U is an ideal of R, let us take U to be equal to 900 by 3. This set contains 0 plus or minus 3 plus or minus 6 plus or minus 9 plus or minus 12 and so on. Right. Now you can see this S is contained in U. This S is contained in U. You can see 0, 0, 6, 6, minus 6, minus 6. So S is contained in U and U is contained in Z because our R is equal to Z. Right. So we have 6 is contained in 3 and this is contained in Z. Right. So if this happens, then R has to be equal to U. S has to be equal to U. But here you can see what is our R? This is not equal to, this is not possible, and also S. What is our S? Again S is also not equal to 3. Both are not equal, right? For example, in the ring of integers, the ideal 6 is not maximal ideal since it is properly contained in ideal 3, which in turn properly contained in I. On the other hand, 5 is maximal, that is what they are doing is it should not properly contain, right? This ideal should not properly contain in some other ideal, but here you can see this ideal is properly containing in 3. So if this happens, then it is not maximal ideal. Suppose if this happens, then this has to be true. But here it is not possible. But 5 is a maximal ideal. On the other hand, 5 is maximal ideal since the only ideal properly contained 5 is I itself. But you can say 5 is a maximal ideal. Why? 5 is maximal ideal. What this set contains? 0 plus or minus 5 plus or minus 10. You cannot find some other ideal which properly contains 5. For example, if you can think of 10, so this set contains 0 plus or minus 10 plus or minus 20, etc. It does not contain 5 or 15. So it is not properly contained in 5. If you can think of 15, you can see this set contains 0 plus or minus 15 plus or minus 30 and so on. You can see this set does not contain 10. So there is no ideal which properly contains 5. For example, if you think of 10, then this ideal contains 0 plus or minus 10 plus or minus 20 and so on. This does not contain 5 or 15. So there is no proper ideal which properly contains this ideal. Suppose if there is some other ideal which properly contains that, it will not be maximal ideal. So in the previous example, we have this is properly contained in 6, the ideal generated by 6 properly contained ideal generated by 3. The ideal generated by 6 is properly contained in 3. But here there is no ideal in Z which properly contains 5. So therefore it is a maximal ideal. But this is contained in R. Right? So there is no if there is an ideal, then this has to be satisfied. If there is no proper ideal which contains, on the other hand, 5 is a maximal ideal since the only proper ideal containing 5 is I itself, right? So the only ideal containing this is the R, only ideal that is containing us R. So if there is no proper ideal that contains 5, then it will be a maximal ideal, right? Again, what about 4? Is 4 a maximal ideal? Suppose if there is some other ideal which properly contains 4, then it will not be maximal ideal. So what about 4? So this gets contained 0 plus or minus 4. Okay, what about 8? Okay, 4 plus or minus 8 plus or minus 12 and so on. Is this a maximal ideal? I can find an ideal which properly contains 4. So therefore it is not maximal ideal. You can see I can find an ideal which properly contains, you can see 4, 8, 8. So I can always find an ideal which properly contains this ideal. So therefore it is not a maximal ideal. Now what about 6? Okay, what about 10? Is this Is this a maximal ideal? So this set contains 0 plus or minus 10 plus or minus 20 and so on. I can find an ideal which properly contains this ideal. For example, you can see this ideal contains 10. This ideal contains 10. So therefore this is not maximal ideal. Now what about 7? Is this a maximal ideal? So this set contains 0 plus or minus 7 plus or minus 14 plus or minus 21 and so on. Now is it possible to find some other ideal which properly contains this? It is not possible, right? If you think of 14, then you will have 14, 28, but you will not get 7. So what we can conclude is, and every element generated, every element A is an ideal. We know that in integers, every element we can generate an ideal. With every element we can generate an ideal. So every A and this A belongs to R is an ideal. This we already discussed. But this will be a maximal ideal if the element is a prime. Is maximal ideal. Right? Clear? So every element can generate an ideal in integers. If the element is prime number, then the element will be a maximal ideal. So you don't think of this definition, so it will be very easy. So what you will do is, an ideal will be maximal ideal if it is not properly containing some other ideal, right? An ideal will be maximal ideal if it is not properly containing some other ideal other than the entire ring. The entire ring surely the whole ring contains that ideal. If there is no proper ideal that it is containing, so we will rephrase this in descriptive form. An ideal, let us say an ideal M is maximal ideal if there is no proper ideal of R, if there is no proper ideal of R containing M, right? That is, there is no proper ideal of R containing M, right? That is, this M is maximal ideal if you cannot find some other ideal which is properly contains M, right? So again repeat, and you can see 6. This is contained plus or minus 12 and so on, and this is not maximal ideal because I can find some other ideal which properly contains this ideal. So if this does not happen, then it will be maximal ideal. An ideal M is maximal ideal if there is no proper ideal contains M of R that contains M. Contains means it should have all the elements, but here I can find an ideal which properly contains 6, right? But suppose if this element turns out to be prime, then you cannot find an ideal which properly contains P, right? So whatever element you take, you cannot find an ideal which properly contains P. So therefore an ideal will be maximal ideal if there is no ideal which properly contains M. A very important theorem that we are going to do. An ideal S, our commutative ring R, is a maximal ideal if and only if R by M is a field. Again, these are some research that we already proved also. So if S1, S2 are ideals, then S1 plus S2 is generated by S1 union S2 and so on. Now we will prove one theorem and then we'll wind up the class. An ideal S of a commutative ring R with unity is said to be maximal ideal. Okay, so this is the characterization for a maximal ideal. So an ideal is maximal ideal if there is no other ideal which properly contains that ideal. So we will prove one theorem, very important theorem. So theorem 4, an ideal S. An ideal S of a commutative ring R is maximal is maximum ideal, maximal ideal, if and only if R by S is a field, that is S is an ideal, then R by S is a quotient ring, right? So if this set turns out to be field, then S will be maximal ideal, then S will be a maximal ideal. An ideal S of a ring R is maximal ideal if and only if R by S is a field. R by S is a field. Now we will assume that it is maximal ideal. Now we will prove that R by S is a field. It's a very important theorem. It's an important characterization for maximal ideal. So whenever you need to check ideal is maximum ideal, so you just form a quotient group R by S. For example, in the previous problem, we have taken R to be equal to integers, and then we have proved that P is a maximal ideal. Then Z, you just form a quotient ring Z by P, then this will be a field, right? So clearly Z by P is isomorphic to ZP, right? And we know ZP is a field. We know ZP is a field, right? So that's why prime will be a maximal ideal. So a quotient ring generated by P will be isomorphic to ZP. So ZP is a field, if P is a prime, and right. So it will prove this. So you just form quotient ring of that ideal. If that quotient ring turns out to be field, then that ideal will be maximal ideal. So proof. So we need to prove, we got to assume that S is maximal ideal. S is maximal ideal. So what I need to prove? I need to prove R by S is a field. R by S is a field. Now S is maximal ideal means by definition, if there is some other ideal U, then S is contained in U, U is contained in R, then S has to be equal to U or U has to be equal to R. Now we will prove that R by S is a field. We will prove R by S is a field, that is, you just take a non-zero element in R by S and then you show that it has a multiplicative inverse. Now let us take an element lit. So what R by S? So we know R by S, right? R by S is set of all those elements S plus A, and this A belongs to R. So this is the structure for R by S, which we defined in the very early of the class. So let us take an element S plus B be a non-zero element in R by S. Be a non-zero element in R by S. Now what we need to prove? We need to prove this element is invertible. Invertible means it has a multiplicative inverse. We need to prove that this non-zero element is invertible. That is, we need to prove that there exists a multiplicative inverse for S plus B. S plus B. Now if B is the principal ideal of R. Principal ideal means that ideal can be generated by single element. Suppose if B is the principal ideal of R generated by B. Generated by B, then S plus B is also an ideal of R. Why? S plus B is also an ideal of R. B is a principal ideal and S is already an ideal. The sum of two ideals is again ideal. So therefore S plus B will be an ideal. If B is an ideal, it's a principal ideal of R, then S plus B is also an ideal of R. Right? S plus B is also an ideal of R. Now since B does not belongs to S, therefore the ideal S is properly contained in S plus B. Therefore the ideal S properly contained in S plus B. That is, the ideal generated by D is properly contained in S plus B, properly contained in S plus B. But we have assumed that it is maximal ideal. So therefore, if this is contained in this, then this has to be equal. Right? This has to be equal. So therefore, it has to be equal. And this is contained in R. So therefore, either this has to be equal or this has to be equal. Therefore, we have is equal to R. So either U is equal to R or R by definition of maximal ideal. So if U is contained, if S is contained in U and U is contained in R, then U has to be equal to R or S has to be equal to U. Therefore, these two have to be equal. So therefore, S plus B is equal to R. S plus B is equal to R. So since 1 belongs to R, so since 1 belongs to R, we must obtain 1 on adding an element of S to an element of B. That is, 1 can be obtained by A plus alpha B is equal to 1, because we can see every element in R can be generated by S plus B. So since 1 belongs to R, so 1 can be written as A plus some alpha B. So S plus B, A plus alpha B, because B is generated here. So I can write 1 as A plus alpha B. So this implies 1 minus alpha B is equal to A. 1 minus alpha B is equal to A, and this belongs to S. 1 minus alpha B, and this belongs to S. So consequently, so we have S plus 1 is same as S plus alpha B, because we know that if we have 1, the idea generated by 1 can be generated is equal to R. The idea generated by 1 is equal to the entire ring R. So this I can write this as S plus alpha B, and this I can write this as S plus alpha into S plus B. So this is by the operation that we defined in the very beginning of the video. So whenever you are multiplying two elements, you need to multiply S plus AB. So here we have alpha B, so I can write S plus alpha B as S plus alpha into S plus B. So we have S plus 1 is equal to S plus alpha into S plus B. That means inverse S plus 1 is the multiplicative identity, and S plus B is the non-zero that we have chosen. So therefore, the inverse is S plus alpha. Inverse is S plus alpha. That is, the inverse of S plus B is S plus alpha. Therefore, R by S is a field. Right. So we have proved that the non-zero element has multiplicative inverse. Similarly, what you need to do is you need to assume that it is a field. You need to show it is a maximal ideal. So again, it's a 3 or 5 lines proof. You can just refer page number 365. Actually, these proofs are a little bit tricky. You need to more than understanding, you need to by heart to write the proofs. So maximum try to understand. If not, you have to by heart 1 or 2 lines. So converse part very easy. Now in the next video, what you will do, you have to do converse part also. For converse part, you refer page number 365 in Krishna series. Again, it follows from the definition. So what we will do in the next video, we will start prime ideal, and after finishing prime ideal is one class, and Euclidean domain is another class. So with that, we will be completing the syllabus. Right. Next video we will see prime ideals and then Euclidean domain. So 2 classes we will finish the course. Thank you.